Hello, I'm Shang. Today I will introduce a framework that can automatically explore the matrix formats and implementation for distributed machine learning and linear algebra computations. Nowadays, data analytics, machine learning, and deep learning have been widely used in many areas. Therefore, many machine learning systems are proposed to support the implementation of those computations. Those systems usually provide programmers an easy-to-use interface and a set of core functions like linear algebra functions. After programmers write their programs in those systems, the systems will compile and optimize those computations and finally execute those computations. The execution can be conducted either on one single machine or in a distributed environment. However, there is a big problem for writing and running distributed linear algebra in those systems. That is, it is very hard for a programmer to decide the proper formats and implementations for matrices and distributed linear algebra computations. I will use a simple example to illustrate this problem. Suppose we have two matrices, A and B. Each has dimensionalities 10,000 by 10,000, and we want to do a matrix multiply with that. We have two machines at hand. In a deep learning system like TensorFlow, here is the code to do the multiplication. You don't need to understand the syntax of the code. A programmer needs to specify the cluster information and manually assign the computation and the data to the corresponding devices. If the computation will be done on two machines, and the programmer wants to use the machines to do a distributed matrix multiply, the programmer needs to manually shard the matrix into submatrix and then assign the submatrix to the corresponding devices. We can find that when the computation becomes more and more complex, it is very hard for a programmer to specify those computations. In another systems, like System DS, which is formerly called System ML, a higher level language is provided. As the code shows here, a user just needs to initialize two matrices and then just write one line of code to do the matrix multiply. The system will automatically figure out the partition of the matrix and then run it on a distributed cluster. However, in System DS, the big matrix will be trunked into submatrix with a size 1000 by 1000. This default size may not be optimal for some computations because different distributed computations may require different sizes for the submatrix to get a decent performance. Finally, database systems can also be used for machine learning. For example, SimSQL, which is a database system, and it enhanced by our vectored matrix data types. A programmer can use this system to do the machine learning computation. A programmer needs to create two tables to store the matrix, and then write SQL code to do the computations. The problem for this system is when a matrix is stored in different formats, a programmer needs to create different schemas of the tables for different formats, and the computations for different formats will need to be implemented differently as well. Even worse, the performance of different implementations can be different as well. Still using the matrix multiply as an example, here is the result for this computation run on SimSQL. The y-axis is the size of the submatrix, and the x-axis is the size of the submatrix, and the y-axis is the totally running time. So we can see with a different submatrix size, the running time can be very different. Therefore, in this paper, we want to design a framework that can automatically explore and select the optimal matrix formats and implementations for linear algebra and machine learning computations. In the remaining part of this talk, I will describe how we achieve our goal. The first step is to formalize this problem as a format exploration problem. The core idea here is we want to separate the logical abstraction from the physical implementation for matrices and computations. More specifically, for matrix data type, a user just needs to specify the dimensionality of the matrix, as well as what kind of computation the program wants to do, for example, matrix multiply. The system will figure out the physical implementation for the matrix types. For example, if it is a block-based matrix or it's a script-based matrix, as well as the physical implementation for the computation, which is the matrix multiply between block matrices or between script matrices. Also, our system should support the matrix transformation between different formats. Here is a specific example for this logical and physical separation. Using the SimSQL code as an example, a user creates a table to store a matrix. It's a 4x4 matrix. And physically, this matrix can be stored in different formats. From the left to right, it can be a single attribute. It can be stored as 4 rows, 4 columns, or for submatrix, each matrix have 2x2 size. Also, the other formats are also supported, like the strips, row strips, column strips, or even single tuples. For the computations, the logical and the physical separation is shown here. For a programmer, he or she just need to write a SQL code called matrix multiply as a user-defined function. Then the system will figure out how to do the actual computation with the actual formats of the matrix underneath. For example, in the physical part, the first piece of code is the code for the matrix multiply between row strip and column strips. And the second piece of code is a matrix multiply between block matrices. The system will figure out which one to use automatically according to the current physical formats of the matrix. Lastly, we will also support the matrix transformations. So suppose we have a matrix, it's a 10 by 10 matrix as the schema shows on the left, and we want to transfer it into a block matrix. Each block has a size 2 by 2. So the SQL code shows this transformation. After we formalize the problem, the second step is to construct a computer graph for the input computations. In the computer graph, each vertex represents an operation or a computation. Each edge represents dependencies between two operations. For example, the vertex V5 have 2 inputs. One is the vertex V4, and second is the vertex V3. The vertex is further divided into 2 types. One is called the source vertex, which means this operations just read the matrix directly from the files. On those vertexes, each will be labeled with the logical matrix type, as well as a physical matrix implementation. Another type of the vertex is the non-source vertex, like V4 to V5. Those vertex has an input with the other vertex, and it is labeled with the logical type of the computation, as well as the atomic computation associated with each vertex. After we have a computer graph, the task for us is to annotate this computer graph, where for each non-source vertex, we will annotate each vertex with atomic computation implementation, such as a matrix multiply between 2 block matrices, or a matrix multiply between strip matrices. For each edge, we will label it with physical matrix transformations between different matrix formats. Here is a specific example to illustrate this computer graph. This computation is a matrix multiplication chain. We do a matrix multiply between matrix A, B, and B, and then multiply with another matrix C. So for the vertex V1, V2, and V3, these read in the matrix A, B, and C correspondingly. And for the vertex V4, it does a matrix multiply. And for the vertex V5, it does another matrix multiply between A, B, and C. So with this information, our task is to annotate this computer graph as the text in the green shows here. We can find that for vertex V4 and V5, we annotate these two vertices with the actual matrix multiply computations with the actual formats specified as row strip, column strip, or single column strip. And for each edge, we will specify the transformations between the two vertices. The third step is to optimize annotation. Our goal here is try to find annotation with a minimum total cost. We can see that there are many ways to annotate a computer graph. So we should find the one with the minimum cost. The cost can be defined in different ways. It can be total running time, total resource requirement, or a budget. After we have a cost, we can define a cost model to calculate the cost of that annotation. Then the task for us is try to optimize the annotation to find the annotation with the minimum cost. In our paper, we use a dynamic programming algorithm to solve this problem. Here is a high-level description of this algorithm. We start from the source vertex, calculate the cost for each vertex one by one in a bottom-up manner. Then we record the minimum cost for each physical implementation at each vertex. After we go through this bottom-up manner, we will get the final output, and then we calculate the sum of the cost of each physical implementation for all of the vertices and select the one with the minimum total cost. After we select the format for the output, we will traverse back in a top-down manner and select the format's implementations for the other vertices with the selected cost. The final step is to generate the code for the selected formats. I will use another example to show this step. This example is for the code generation for matrix multiply. Suppose we select the formats for matrix A and B as a block-based matrix, as the schema shows here. And internally, the system has this template to specify how to do the block-based matrix multiply. The text in the right in the SQL code represents the variables of the template. So our system will replace the variables with actual attribute names in the table, and then the actual SQL code is produced. This code is then shipped to the execution engine to execute. We implemented our ideas on two systems. One is the SimSQL. It's a distributed analytics relational database prototype. Another one is a Plenty Compute. It's a high-performance distributed relational engine. We did 3 sets of experiments to show the efficacy and the efficiency of our implementation. The first experiment is to compare the auto-generated code to the code that is written by the expert users of the system. The second experiment will compare the auto-generated code with the code that is run on the other systems. And the third one will be a examination for the optimization time of our algorithm. In this talk, I will describe 2 examples from the first 2 experiments. For the comparison with the expert code, we compare 3 implementations. One is the auto-generated code, that is code generated by our framework. Another one is a code we call human written code is written by an expert user of the system. And the third one is a code where every matrix is stored as a matrix, as a block matrix. It's a most straightforward way for distributed computations. We tested 3 computations. One is a feed-forward backpropagation neural network. The other two is a blockwise matrix inverse and matrix multiplication chain. In this talk, I will focus on feed-forward backpropagation neural network. We run the experiments on a 10-node Amnon EC2 cluster. Here is the result. We test on a 3-layer feed-forward neural network, and the sizes of each layer is shown in the top of this slide. On the result graph, on the x-axis is the layer size of the hidden layer. So we try different layer sizes of the hidden layers. And on the y-axis is the running time for updating the weight matrix for the second layer for one iteration. We can find that for all of the hidden layer sizes, the auto-generated code can outperform the expert code and the code that is written in all block-based manner. We can also find that when we increase the layer size, the auto-generated code can have more performance benefits. It is because it will produce different implementations according to different characteristics of the input data. We also compare the auto-generated code with more expert code. So we recruit 3 additional users. They have different background of machine learning and the system. So we give them a set of candidates formats to select, and they will choose one according to their background and experiences. And then we will construct the SQL code from their choices. We can find that in this experiment, again, the auto-generated code can outperform the expert code that is generated from the expert users in machine learning and the system. The second side of experiment is a comparison with the other systems. In this experiment, we compare Pllinic compute with PyTorch and system DS. And also for Pllinic compute, we try to explore if the sparsity can help the implementation or not. The computation we test is a 2-layer feed-forward backpropagation neural network, and we test on a real Amazon dataset. Again, we run experiments on a 10-node Amazon EC2 cluster. Here's the results for the system comparison. Again, the size of each layer is shown on the top of the slide. On the result graph, the y-axis is the running time of the one iteration, including one forward pass and one back propagation pass. And the x-axis is the layer size. We try different hidden layer sizes again. The left 2 columns is the result for Pllinic compute. We can see that it can outperform the PyTorch and the system DS. More interestingly, if we introduce the sparsity support in Pllinic compute, and we let our framework to explore the sparsity in the selections of formats, the running time can be further decreased. To conclude, in this paper, we propose a framework to automatically and systematically explore the matrix formats and implementations for linear algebra computations. We formalize the problem as an optimization problem and solve it with a dynamic programming algorithm. We create a query rewrite engine to automatically generate SQL code for the selected formats and implementations. Finally, we conduct a comprehensive set of experiments, and the results show that the code generated by our framework can outperform the handwritten code. Thank you.